Welcome to Techno Sapiens.
Hey everyone, welcome to this explainer. Okay, let's dive right into a massive engineering mystery that is literally hanging right above our heads. Every single day, we walk under these giant transmission towers buzzing with unimaginable power. But why exactly are they built this way? Well, understanding this actually unlocks one of the smartest technological solutions in human history.
Think about this enormous gap for a second. In your living room, you've got a safe, perfectly manageable 230 volts powering your television and your toaster. But then, just a few streets away, you have hundreds of thousands of volts roaring through those heavy-duty wires.
It totally makes you wonder, right? I mean, why don't power companies just send electricity straight to our homes at 230 volts right from the get-go? Wouldn't that be infinitely easier? Wouldn't it save us the trouble of building massive towers and keeping all that dangerous high voltage so far away from the ground? Why go through all the trouble of jacking the power up to hundreds of thousands of volts, only to have to meticulously bring it all the way back down again before it hits our walls? Let's kick things off with Chapter 1, the energy loss problem. To really grasp why we do this, we have to look at the massive physical challenge of moving electricity. Imagine a power station, say, 200 kilometers away. As electricity travels that huge distance, it definitely isn't a free ride. It actively fights against the wire's physical resistance, kind of like electrical friction. And a huge chunk of that precious energy just leaks out into the environment as heat. You know, you actually experience this on a tiny scale every day. Ever notice how your phone charger gets warm to the touch? That warmth is literally electrical energy being converted into heat instead of going into your battery. Now, for one single charger, no big deal, but if you scale that up to a whole city, that heat would waste astronomical amounts of energy. If too much power gets lost along the line, less actually reaches our homes, and power companies would go absolutely bankrupt trying to burn enough fuel to make up for the loss. Which brings us to Chapter 2, blame it on current. A lot of folks assume that high voltage itself is what causes energy loss, but the math tells a totally different story. The formula for power loss is current squared times resistance. That little squared symbol, that is the real villain here. It reveals that voltage isn't the problem at all. Instead, even a tiny, tiny increase in current causes massive exponential energy losses. It's basically a compounding disaster for efficiency. Think of it like trying to forcefully jam way too much water through a super narrow pipe. When water flows normally, it's smooth sailing. But if you try to force excess volume through that exact same space, the friction absolutely skyrockets. The pipe is under immense stress, and you're wasting tons of energy just trying to push it through. Well, electric wires work the exact same way, creating wasteful, expensive heat when the electric current is too high. So, how do we fix it? That's Chapter 3. The smart solution. Engineers couldn't just rewrite the laws of physics, obviously, but they did figure out a remarkably clever way to manipulate the math. See, electric power is simply voltage multiplied by current. That gave engineers a phenomenal choice. To deliver the exact same amount of power, they could either use low voltage and high current, or they could completely flip it, use high voltage and low current. And since we just learned that current is the main culprit causing all that heat, engineers realized they could basically crush that heat-causing current by massively cranking up the voltage instead. Let's put this into perspective by comparing the delivery of 1 megawatt of power. In a standard setup, if you push it at 10,000 volts, you're forced to deal with 100 amperes of current. That's a ton of heat. But look at this brilliant engineering workaround. By boosting the voltage 10 times, all the way up to 100,000 volts, the current plummets down to just 10 amps. And the crazy part? You are still delivering the exact same full megawatt of power. So, 10 times higher voltage means 10 times lower current. And remember that power loss formula where current is squared? Because of that math, a massive 10-fold drop in current means the wasted heat practically vanishes. The energy losses become dramatically smaller. This neat little mathematical trick is exactly why high-voltage transmission is so incredibly efficient. Okay, moving on to Chapter 4, Safety and Transformers. This brings us right back to your house, and finally answers our very first question. Why on earth can't we just plug our TVs into 100,000-volt outlets? Well, safety. High voltage is fantastic for efficient cross-country travel, but it is wildly dangerous for people. It would instantly fry everything in your house. That is exactly why we rely on step-by-step transformers. Before electricity ever hits your neighborhood, it passes through massive transformers just outside of town to drop that extreme voltage.
Then, those smaller transformers you see up on utility poles step it down even more. By the time it actually reaches your home, it's a completely safe, manageable 230 volts. So the next time you're driving and you look up at those giant transmission towers stretching across the horizon, just remember, they aren't carrying high voltage to give you extra power. They're just doing it to completely eliminate electrical friction. Without this frankly brilliant high-voltage engineering solution, modern cities simply couldn't receive electricity efficiently over long distances.
But wait, think about those transformers we just talked about. How exactly do they change voltage up and down without breaking the laws of physics? I mean, how can a simple metal box physically step power down from 100,000 volts to 230 without losing everything along the way or creating extra electricity out of nowhere? Well, that is a fascinating mystery, and it's exactly what we're going to unpack in our next explainer. See you then.